Hi everybody, my name is Chris. I know I'm sure to a lot of you I look like a teacher or a professor, but I'm just a student like you. And in fact, next fall, I will be studying earth science and geology at the U of M. Why am I doing that? It's because I love the earth, I love the landforms, the hills, the valleys, and I love maps. I love all kinds of maps and more maps, which makes gradient and the directional derivative a perfect section for my teaching project. Of course, there'll be numbers and there will be equations. This is multivariable calculus after all. But my mind tends to run more with the geometry, with the pictures, with the physical look of things than the algebra of it all. I wade through the algebra. You guys are all better at this than I am. But I intend to give this subject a good physical and visual representation, and I hope you find it helpful for understanding what gradient and directional derivative are and what you can do with them. So our text, as the way it's laid out, starts out with the directional derivative and then moves on to gradient. Khan Academy, which I use all the time and I love it, works the other way around, and I'm going to do that too. It all comes together in the end, and it all involves partial derivatives and vectors, which is what this class is all about. And we will start with the gradient. And gradient is exactly what it sounds like. It's a measure of slope. It's a measure of steepness. Or in the case of a function, it's a measure of the rate of change. And it works just like a regular derivative in Calculus 1, you know, as the rate of change or the tangent line to a function at a point. Only now we're in 3 dimensions. We're seeing things as surfaces go. And anyway, we've all used derivatives before in this way. And in multivariable calculus, we use partial derivatives. And our gradient in this context will end up in vector form, which means it not only indicates slope, but direction as well. In this case, it is the direction of steepest ascent, and I will explain that in a minute. But hey, I promised you pictures, so let's look at pictures. So we'll start here in Yellowstone National Park with the famous rock formation called Half Dome. It looks just like this, I assure you. It doesn't really, but let's just say this is our half dome, and its surface area has a function of, say, 9 minus x squared minus y squared, which makes it a giant elliptic paraboloid made of granite. Anyway, every point on the surface has a gradient or slope or steepness, whatever. Wherever you are, let's say if you're climbing this mountain, hopefully you want to be up here where it's not steep at all. But in order to get there, you have to be somewhere here. And if you were at that point and wanted to know which way is up, the gradient vector would tell you that. We'll calculate this vector using partial derivatives, and it's going to look like this. Here's our function, and here is our formula for gradient. This little guy right here, this little upside down delta, which we call del, is the symbol for gradient. We got our function, and we have our partial derivatives. Partial derivative in function of xy, partial derivative for x becomes our I component, and the partial derivative with respect to y becomes our j component. So let's take this function at this point and let's compute the gradient, and then we'll go back to our pictures and we'll find out exactly what that means. So we take the partial derivative of x, and just a quick reminder of how that works. 9 is a constant, so that goes out. Negative x squared becomes negative 2x. And y is a constant, so that goes out of our x term. Then we take our partial derivative with respect to y. We have a constant that goes out. x squared we treat as a constant because there's no y, so that goes out, and all we're left with is negative y squared, which the derivative is negative 2y by the power rule. At the point negative 1, we plug those numbers in, and we get this, and this is a vector, and it is our gradient vector. It is 2, negative 2, and we can also calculate the magnitude of that vector using our magnitude formula, square root of 2 squared plus the square root of 2 squared plus negative 2 squared, which comes out to 2 times square root of 2. So we have, basically we have, this is our gradient vector, and this is our magnitude of our gradient vector. What does this number tell us? This number tells us the direction, as I said, of steepest ascent. This number tells us the slope. Now if we go back to our mountain, and we can look back, we can look at it from the sky. It'll look like that. Although it's half dome, so we're using half of it, whichever half, it doesn't matter. It's an elliptic paraboloid. Let's take our original point, negative 1 and 1. So we're negative 1 in the x direction, we're positive 1 in the y direction. That puts us right here. And we compute that through the gradient, and we came out with the vector 2, negative 2. That vector would look like this. Positive 2 this way, negative 2 this way, and essentially it points directly towards the top. And what do you know? We have our gradient vector. We have 2 times the square root of 2, which is the magnitude, which you could represent this way, but essentially it is also the slope at this point, which if we were down in our mountain might put us somewhere right about here. And our vector would point to there. Let's come back with another example and compute gradient. Okay, so here we're going to really quickly just run through another example of how to use the gradient formula to derive a gradient vector from this function, x squared y plus x, and we will find the gradient at the point minus 1 minus 1/2. So here again, you see here's our little gradient del operator, and here's our formula kind of cleaned up in this thing. Partial x is the I vector plus partial y is the j vector. So we take the partial with respect to x, and we get 2xy plus, this becomes 1, and partial with respect to y is just this constant, and this goes out, so we just end up with x squared. And you know, we could also put that in our vector brackets. That's my cat. Anyway, if we input these into our del gradient operator, we output this vector 2, 1, and like I said before, that is your direction of steepest ascent of our function. That is where your function changes the fastest, where you get the most z for your dx and your dy, if you want to talk like Leibniz about it. But that's how that works. And if we take the magnitude of our vector, we get 5, which is that is actually the slope of the function at that point. And we can do a quick visual representation on our board right here. This is what Wolfram alpha gives us for our our sky view, basically, as it was, of this function that we have there. And the point we took was -1, -1/2, which puts us right here. -1x, -1/2y. Set that point. And if we run those numbers through our vector, we come up with the vector 2, 1. So we go 2 in the x direction, which would put us here, and 1 in the y direction, which would put us up here. And our vector would actually point in this direction. And what you will notice here is that our vector points basically uphill. If we were to do this for a bunch of points, we would end up with a vector field. And this is the interesting part, and you'll see this in physics when you do magnetic fields and when you do electric fields, is that all of our gradient vectors will essentially, without paying attention to magnitude, will be perpendicular to our contour lines. And you could just keep doing that, and all the little vector lines would point there. And you could do them, you see them, sometimes it looks really messy if you put the magnitude of the vector lines there, so a lot of times they'll just make them different colors. So this would represent that color, but you get the idea. It's all perpendicular to the contour lines. It is the direction of steepest ascent, where your function changes fastest in the positive direction. So let's set up an example of directional derivative, and we'll come back and do that. So we will just do a quick explanation of what the directional derivative is, and then we're going to do an example. So we'll look at our half dome again, and you could take any point on this mountain. We'll say right here. Here's our little climber guy, and we already know the gradient would point directly towards the top, or the direction of steepest ascent. But what about this direction? What about this direction, or this direction? What if there are no handholds? What if you were hungry, or you missed your mother and you need to get down? None of that matters to us, but what matters is what happens to the function at any of these directions, and we call that the directional derivative, and it looks like this. In our textbook, they use this notation, big D sub u, for directional derivative. What we have is the partial of x of our function xy times a, and that comes from our direction vector that we have chosen, or was chosen for us, and the partial of y of our function xy times b, the j part of component of our vector. And if you will notice, if you extract this ab into a vector and you extract this, what you have is the gradient of our function dotted with the vector AB, and we can even simplify that. What we want to do is take AB to be a unit vector. You don't have to, but it always ends up being a unit vector anyway, so we just figure that out that way, and we take the gradient dotted with the unit vector in the direction, and that gives us our directional derivative. And I'm not going to use this anymore because I left the cap off. And I'm going to set up an example, and we'll come back and work on that. Okay, an example of the directional derivative. We're going to go back to our function of our elliptic paraboloid, which I used to describe our mountain, 9 minus x squared minus y squared. Remember our directional derivative formula. You can back the video up if you don't, but I'll explain what we're doing. We will take a point on our function 1, 1 for simplicity. We will take a directional vector 4, 3, and that is the direction that we will point at that point 1, 1. We're going to go ahead and make that into a unit vector, which, if you remember, this is the formula for the unit vector. We take the magnitude of the vector, 4 squared plus 3 squared, its square root is 5. And by this formula, we divide each component of our vector. And that is our unit vector, 4/5 I and 3/5 j. We took the gradient and dotted it with the unit vector, and that's basically what the directional derivative is. The gradient minus 2x minus 2y comes from the partial derivatives of x and y, and it is a vector. And if we solve it for this point, we come to -2, -2 is our gradient vector at that point, which we dot with our unit vector 4/5, 3/5, and we come up with a -8/5, -6/5, and this is a scalar quantity because it's a dot product, and so just subtract one from the other and you get -14/5, which is the derivative. It is the change in function in the direction of this vector at this point. It is our directional derivative. The last thing we're going to do is a directional derivative, which also includes a gradient, for a function in 3 variables. Okay, let's do one more example of a function in 3 variables, and we will find the gradient and the directional derivative of the function f of x, y, z is x sine of y, z. We will find the gradient at the point 1, 3, 0 in the direction of the vector I plus 2j minus k. So, in order to find the gradient, first of all, we take the partial derivative with respect to x, and that is basically x times this constant. So the x goes out and we're left with sine of yz. Next we have this constant and the derivative of sine of yz with respect to y, which is the cosine of yz, and by the chain rule we take out this constant, or the derivative of yz, which is z with respect to y. So we have xz cosine of yz. We do the same thing with respect to z, and you know how that works. Basically you end up with xy cosine of yz. Our partial derivatives of the function in vector form is the gradient of the vector. Next we take the vector v, and we need to find the unit vector that represents that. So by our same formula, we take the magnitude, here's our vector, over the magnitude of its vector, 1 squared plus 2 squared plus -1 squared all comes out to root 6, and our unit vector u looks like this: 1 over root 6, 2 over root 6, and -1 over root 6. And the last thing to find the directional derivatives, if you take the dot product of the gradient times the unit vector, and that's pretty easy to do. Here's our gradient vector, and here's our unit vector. Dot product is 0 times 1 over root 6, which is 0. 0 times 2 over root 6, which is 0, and added to 3 times -1 over root 6, which is -3 over root 6, which with 0, 0, 0 basically becomes our solution, our scalar quantity, negative 3 over root 6. And again, that is the change in our function in the direction of this vector here at this point here. Thank you very much for watching, and enjoy your learning experience from here on.